Hello everyone, in this video we're going to take a look at a topic called binary search and also the problem technique called binary search and answer. So before we get into binary search, let's first consider a problem or just like a question or a demand, I don't know. So if you're asked to locate a number within a sorted array, so remember it's sorted. So how would you do that? So here is an example of array. So you have 1, 5, 10, 22, blah 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 blah. So if you are asked to locate a variable called x, how would you do that? Of course, you're gonna, the most intuitive way and probably most common way is just like look one by one. So you go from, um, you go from the first one, second one, third one, and so on until you find the element that matches x. To be honest, that's not a bad idea if you're if you're trying to find the variable that is like 5 or 1, you're only gonna look at like one element or two element. That is really good. However, if you're a bit unlucky, you get like x of 9, then that's a bit sad because you have to look through 8 elements, and that's just not good. So another approach to this problem is binary search. So as we have stated, our array is sorted. It means it's in order, in increasing order. So all the element is uh, greater than its greater or equal to its like element on the left and smaller than the element to the right. So you can just choose the middle one like this one. Then you can compare your value of x to the number. So if your x is bigger than that number, then you know your x has to lie in this range. Because if your x is bigger than the number and the numbers on the left side of the middle number is always smaller than that number, then there's no way x can be among those. So x has to be in this range. And that is the essence of binary search. Then you can just search, look at only this range, and continue this action. You still take the middle one, and you compare x with it. If x is the number, then you just get the answer directly. You get the location directly. Otherwise, you know the next range of x possibly gonna be. And you can just continue the action repetitively until you find the answer. To be honest, that's a really fast way. So in the worst case, you will have the time complexity of log n. So n is the length of the array. So let me switch a pen. Pen, okay. So it doesn't really sound that fast, but it's actually really fast. So when you have an array of 10 to the power of 9 elements, so it's probably a 1 with a bunch of zeros, so it's a really big number. All you need to know is it's super big, but we only need to search for 30 times. Like we got only need to look for 30 elements before we find the like actual value, because we just cut like half of the possible position off every time we do it. So maybe the first time we can cut one part off, like 50% off, and we can just repetitively continue this super efficient way until we find our value. And I think it's so good because no matter how long the array is, no matter how large the data size is, you can always eliminate 50% every time. Okay, that's for the binary search algorithm. Now we move to binary search and answer. So binary search and answer is a bit different from binary search because it's rather a problem solving technique. It's also an algorithm, of course. So below definition is from USACO guide. which is a super good website for learning algorithms. So they conclude binary search on answer as, let's say we have a Boolean function f of x. Usually in such problems, we want to find the maximum or minimum value of x such that f of x is true. Similarly, blah blah blah. You can read on by yourself. Okay, I assume you have already read everything, then I'm just gonna continue. So that may sound like a kind of boring description, so I just gonna like explain it with like an example. So let f of x, the f function, means represents if there's enough water to drink, and x is the amount of water. So in this case, uh, you are trying to look for the minimum amount of water that's enough to drink. So in this case, we can just choose like um, we have like a range of possible uh, answers. So we just pick the middle one. We see if if our function returns true or not. If it returns true, it means we have enough water to drink if we have like x liters of water. And in this case, all the uh, number greater than x is also valid, and it's because it's monotonic, and in this context it means if you have more than x liters of water to drink, that's enough. You when x is enough, like when if 5 liters of water is enough for you to drink, then 10 liters of water is definitely enough as well. And that is like just like array being sorted. Here it's kind of like the idea as well. So we just take the middle one, we see if it's enough, if the function returns true. If it returns true, then we're just gonna look for the below ones because we are trying to look for the minimum value. Otherwise, we know if it's false, then it's just gonna be in this part. Then we can continue that action repetitively until we find the actual answer. So there are two ways of implementation. I mean, there are tons of ways to implement binary search, and um, below here is just like two of my ways to implement. The first one is to find the minimum value uh, of x, that if you plug in x to a function, the function will return true. And the function is different for different problems, and it's usually like you write different functions under like uh, for different problems. So yeah, and this one is to find the maximum value that f of x is true. I see a lot of implementation of binary search online, and you can just look at them as well. But generally, if you have one copy, and that's good. I recommend you to have like a few implementation reminded in your mind for contests, because I think binary search usually has some like people usually make some off by one mistake, which is kind of like avoidable, but it's a pity to miss a point in the contest just because a little mistake. Okay, so let's look at a example problem from USACO. It's called Angry Cows. You can search the title and try to do the problem on your own. I really recommend you to do that. And I also pasted the problem statement here. But I'm just gonna continue. You can pause the video to look at it, of course. So I assume you have already looked at it, and I'm just gonna go over the solution and the explanation. So first, there are a few observations to look at. The first one is this problem is a monotonic condition. It means if x works, then all the value above x works as well. So if the blast radius of 5 works, then blast of radius of 10 of course works as well. If blast radius of 3 doesn't work, then any number below 3 doesn't work as well. So we know we can implement binary search in this question. And this question wants us to find the minimum blast radius. Yeah. So for our function, what we're gonna determine is whether we have enough cows to eliminate all the hay bales. So we can calculate the number of cows needed with blast r of x. So that's kind of grammatically wrong, but uh, so I'm just trying to say like that. This function will determine whether we have enough cow to eliminate all the hay bales. So if we have too little, so we're just gonna return false. Otherwise, return false, return true. It means we are good. Our x is good. And here's my implementation. So let's take a look at the main function first. So first, I just gonna scan in all the values, and then I sorted the array. Here I implement the binary search, and for this problem, I think the probably difficult part is the implementation of the function f. So the way I calculate the number of cow required is by assigning cows in a way that it can eliminate as many as hay bales as possible. So we know when a cow land on the ground, it will create a blast radius around it. So we're gonna go left and right. So we're gonna try to take that observation into this account. And for each hay bale, we want to wait as little blast as possible. So assign the left blast boundary to the left to the current hay bale, like the leftmost hay bale. Then we just gonna skip over the hay bales within the range of the first blast, and we move on to the next hay bale that is out of the blast of the previous cow, and we still just put the left boundary to the hay bale, and we continue this action. And each time we place a cow, we just increment our cow required number, and finally we check if the number is greater than our like cow we have, the number of cow we have. So if it's greater, we know it's impossible, and if it's smaller or equal, we know it's good, so we return true. And that is for this problem. So I hope you have learned something about binary search in this problem, and I will post more videos of algorithm in future as well. So thank you for watching. Bye.